Section 3.2, finding domain and range from a graph. So when you're looking at a graph of a function, you will be able to determine the domain and range of the graph. The domain of the function is basically all of the x values that the function can take. So you're going to scan the graph from left to right, and you're going to determine where does the graph start and where does it end, making sure you're paying attention to the holes in that function. For example, the domain of the graph given in this example is from -3, but the -3 is not included, and it spans over the interval, and it stops at 1, and the 1 is included because the dot is closed, and the graph goes from -3 to 1, including 1 as well. So that is basically the domain of the function. The range of the same function can be determined by scanning the graph from bottom to the top, again, determining all of the y values that the function can take. Notice here how the graph of this function starts from -4. So it starts from -4, and the -4 is included, and it goes all the way to 0, to y equals 0. So this point is basically y equals to 0, and the 0 is included as well. Some of you might be confused with this hole right here. However, notice how the graph touches right here, the 0, passes through the 0, so it takes the value 0, despite the end of the graph here or the beginning of the graph being a hole, which affects the domain, but it does not affect the range. So hopefully that is clear. Similarly, you will be able to find the domain and range for all of the basic toolkit functions in section 3.1 if you would like to. Let's answer some questions. Can the domain and range of a function be the same? Yes, the function might have the domain and range are the same. The famous example is the function f of x equals x. The domain and range is all of the real numbers. All of the real numbers are the domain and range of that function. Can the domain and range of a function not intersect at all? Yes, it happens. Very rarely though. If you define a function such that the domain of that function is the set 1, 2, 3, and the range of the function is 4, 5, 6, then you can define this function such that f of 1 equals 4, f of 2 equals 5, and f of 3 equals 6. This is basically a function we defined, and notice how the domain does not intersect with the range. There is no common numbers that they share, but there is a function defined with these conditions right here. So it is possible to have the function, the domain and the range of the function not intersect at all, but in rare occasions, of course. Piecewise functions or piecewise defined functions and graphing piecewise defined functions. Sometimes we come across a function that requires more than one formula in order to obtain the given output. For example, in the toolkit function, we introduced the absolute value function. F of x equals the absolute value of x. If we input 0 or a positive value, the output is the same as the input for all of the positive x's. So all of the positive numbers, including the 0, if you input them into the absolute value function, you will get the same output. However, if you input a negative value, the output is the opposite of the input, or in other words, you're going to get a positive value. So that is what we were talking about, the absolute value function. Because this requires two different processes or pieces, the absolute value function is an example of a piecewise function. So a piecewise function is a function in which more than one formula is used to define the output over different pieces of the domain. Here is an example. If you have the function f of x defined as x squared for all of the x's that are less than or equal to 0, and it is equal to 4 for all of the x's that are between 0 and 2, inclusive of 2x exclusive of 0, and it's equal to x minus 1 for all of the x's that are greater than 2. So it's defined over 3 intervals. If you imagine that, and if I assume there is a 2, there is number 2, the function is going to be defined as follows. So the first piece is going to be for all that are less than or equal to 0, so all of these numbers. And then from 0 to 2, not including the 0, it's going to look like this, but the 2 is included. And then anything above 2, it's going to be a different one. So if I code color here, the yellow part is right there. Let me actually remove the previous highlighting. So if I am trying to color code, this is the yellow part, and then the green part is the last one. So it's defined over 3 intervals with 3 different formulas. If we want to find f of -3, for example, f of -3, we have to determine where -3 is going to be. So -3 happens to be in the pink interval, which means in order to determine f of -3, we have to use the pink formula in order to determine that. So f of -3 is equal to -3 all squared. So we took the pink formula and we substituted x with -3, which is going to give me 9. F of 0. Notice how the first interval takes the 0, which is the pink also. So the 0 is here, and the pink takes that as well. So I'm going to use the first formula. F of 0 is equal to 0 squared, which is equal to 0. F of 1 happens to be in the yellow interval. So I will use the middle part. So in this case, f of 1 is equal to 4. There is no x to substitute for 1, so I'm going to leave it like that. F of 2, notice how 2 is included in the second interval. This second interval right here, so the 2 is included here. So I will use the second formula, or the the yellow formula. So f of 2 is equal to 4 as well. And then f of 5, notice how 5 happens to be in the green interval. So I will use f of 5 equals, I will use the last formula, which is 5 minus 1. So I will substitute x with 5. You will get the answer equals to 4. So as you can see here, we defined this function over some intervals with different formulas, and it gave us different answers for these different numbers. And similarly, you're going to be able to graph the piecewise function. Let's say we want to graph the first function, f of x is equal to -x minus 1 for x less than or equal to 0, and it's 1/2 x plus 2 for x is greater than 0. So what I like to do is first to determine the intervals. So the intervals break at this point, which is basically x is equal to 0, okay? Now, I'm going to create two tables. One table is going to include values that are less than or equal to 0, and another table that is going to include x is greater than 0. So I will create a table of values for the first one, where x here and f of x is here, and the part is -x minus 1 in this case. So I'm going to choose the values, including the border value, so this 0, and I'm going to include it with a box, so I know that it is included in this case, and then I will substitute it in this formula right here. So -0 minus 1 is -1. So the first point is 0 and -1, 0 and -1, and that is included in the graph. Next, I'll choose another point that is less than 0. So I'm going to choose -2. And then if you plug -2 in, you'll get -2 minus 1, which will give you 2 minus 1, that is 1. So the second point is -2 and 1. -2 and 1. Right here. And then you're going to graph this part of the equation, which is basically a line in this case. Next, you're going to create another table for the other interval. So here is another table of values. Here is the x, here is the f of x, which is 1/2 x plus 2. And then you're going to choose the border point, which is 0. And in this case, it's x-inclusive, so I'm going to surround it with a circle, indicating that it's not included. However, I would like to see the behavior of the function at this point, and then if you plug it into, you will get 1/2 0. 1/2 times 0 plus 2, we will get 2, so the first point is 0 and 2. 0 and 2 is right here, but it's x-inclusive or x-secluded, so I'm going to surround it with an open circle. Now, This is a line, the second half is another line, so I will need another point. We're going to choose a point that is greater than 0, so that point is going to be, let's say, 1. 2 to be easy because we want to cancel the 2. So we're going to choose 2. We'll have 1/2 times 2 plus 2. That is 1 plus 2, which is 3. So the second point is 2 and 3. 2 and 3 is right here. And I know that the second graph is a line as well, so I'm just going to connect that line. So now you have a graph of that function. Similarly, you can graph the 3 pieces function with the same manner. So as you can see here, the border points are 0 and 2. So you can basically determine these border lines first, or where the function is cut. And then here is a 2. So now I have 3 intervals. Now I will create 3 table of values. So here is the first table of values, x and x squared. So which is the first part. And I will choose the 0 as the first point because that is the border. And the 0 is included, so I'm going to put a box. If you plug it in, you get 0 as well. 0 squared is 0, so the first point is 0 and 0. And it's included, so I'm going to put a closed circle. Then I will choose another point that is greater than 0. Sorry, it's less than 0. I will choose another point that is less than 0. So I will choose negative 1, negative 2. Negative 2. If you plug it in, you get negative 2 squared, which is 4. So you get the point negative 2 and 4. Negative 2 and 4 is approximately here. And I know this is quadratic, so it's going to be a curve like that. So that is the first piece of function. The second part, I will create the table right here, x and 4. And in this case, I have 2 points that I have to test, 0 and 2. The 2 is included and the 0 is excluded. When x is 0, y is 4. When x is 2, y is 4 because y is a constant. So it is always going to be 4. So the first point is 0 and 4. 0 and 4, it's right here. I'll do it in a different color. And the 0 is not included, so I'm going to put an open circle. 2 and 4. When x is 2, y is 4. And it is included, so I'm going to put a closed circle. And that is basically a constant line. And then the last one, I'll put x and then x minus 1. I will choose the 2 and then anything greater than 2. So 2 and 2 is excluded. And then I'll choose, let's say, 3. So if you plug in 2, you will get 2 minus 1, which is 1. So the first point is 2 and 1. 2 and 1 right here, and it's excluded. And then the other point is when you plug 3, you get 3 minus 1, which is 2. So 3 and 2. 3 and 2. And it's basically a guide. I know this is a line, so the line is going to continue forever to positive infinity. And that basically is the graph of the second function. Write the domain and range for both functions. So the domain of the first function is all of the real numbers, so from negative infinity to positive infinity, because as you scan the graph from left to right, you will notice that the graph spans all of the real numbers. The range, we scan it from the bottom to the top, so you notice that this is the beginning of the graph, and then it goes all the way to positive infinity, including all numbers. So in this case, the range is all of the real numbers the range is from negative 1, inclusive of negative 1, all the way to positive infinity. The second graph, the domain of the graph of the function, or the domain of the function, is basically all of the real numbers, since the graph doesn't have a beginning on the left and then it continues to the right to positive infinity. So the graph is from negative infinity to positive infinity. The domain is from negative infinity to positive infinity. The range of the function, we're going to scan the graph from the bottom to the top. We see that this is the beginning of the graph. Y, is equal to 0. And then it goes all the way to positive infinity. This graph basically covers everything. So we don't have to worry about these holes in here because this graph covers that hole. So it is going to be from 0, and the 0 is included, all the way to positive infinity. And that would be the range of the second function. Can more than one formula from a piecewise function be applied to a value in the domain? The answer is no, because if you apply it to more than one piece, you're going to get two different answers, which means one number from the domain goes to two numbers or more. Let's say I have B, C here, goes to two values in the range, which is going to make it not a function. So in this case, if this was true, then we will end up with something that is not a function. So this is not possible. Actually, the last part is not possible. And this concludes section 3.2. If you have any questions, don't hesitate to contact me.